Hi again. Let's continue our study of string equation. Today we solve the initial value problem for the string equation. So the string equation is second derivative in t minus second derivative x equals 0. And we add two initial conditions. This is a second order equation in time. So we need two initial conditions. As usual for mechanical systems, we have to give initial position and initial velocity. So yeah, I write u of x0 equals f of x, and the velocity ut of x0 equals some function g of x. Now f and g are given functions. Okay, so let us solve this equation. So what I'm going to do now, I want to find the formula which gives solution of this problem. So the problem again consists of equation and two initial conditions. X in R, so x in the whole x-axis, t in R plus. R plus is positive semi-axis, so t more or equal than 0. So we know that every solution of string equation has the form u of xt equals v of x plus t plus w of x minus t. Last time I derived this formula. So we have to find this function v and w. To this end, we substitute it into the initial condition. U of x0, if you take t equals 0, equals v of x plus w of x. And this should be equal to f of x. We see this. Ut of x0, we have to differentiate it with respect to t, equals v prime of x, t equals 0. Now if you differentiate this, it is w prime of x times minus 1, because here is minus t, minus w prime of x. And this is equal to g of x. Now, so we have to find u and v from this system of two equations. Now, let us differentiate the first equation. And we'll have u differentiate the first equation, and we have v prime of x plus w prime of x equals f prime of x. And the second, v prime of x minus w prime of x equals g of x. So for any x, we have the sum and the difference between v prime and w prime at this point, and so if you add it, multiplied by 1/2 and this 1/2, and add up, then you have v prime of x, and w prime will cancel, equals 1/2 f prime of x plus g of x. Now if you multiply the first equation by 1/2 and the second by minus 1/2 and add it up, then this term v prime will be killed and remains w prime. W prime of x equals 1/2 f prime of x minus g of x. From here we restore f, v and w. V of x equals integral 1/2 f prime of x plus g of x dx equals 1/2 f of x plus 1/2 g of x plus c1. So what is g capital of x? Equals integral gx dx. It is a primitive function of g small of x. Yes, and we have many such primitive functions. They differ by a constant. Now take some of them. It is not principal which one. And one moment, I will make some space. I think you remember what was written here. So v of x equals 1/2 f of x plus 1/2 g capital of x plus c1. W of x by the same reason equals 1/2 f of x minus 1/2 g capital of x plus c2. Now what can you say about c1 and c2? And let me write u of x 0 equals v of x t equals 0 plus w of x equals fx. This term will cancel, plus c1 plus c2. But it should be equal to f of x. No, this means that c1 plus c2 equals 0. Now, if you take any c1 which c1 and c2 such that their sum is 0, then after all it will not change the sum of v plus w. This means that we can take C1 equals C2 equals 0. And so you have V of x equals 1/2 f of x plus 1/2 g of x. Simply so, C1 is 0 and W of x equals 1/2 f of x minus 1/2 g capital of x. This is fine. And now, so we found these functions. And now we can write the answer, solution of our equation. U of xt equals V of x plus t, yes, plus W of x minus t equals 1/2 f x plus t plus 1/2 g x plus t plus 1/2 f x minus t minus 1/2 g of x minus t. So I have to substitute here, instead of x, substitute here x minus t. No, let me write it again. 1/2 f of x plus t plus f of x minus t plus 1/2 g of x plus t plus g of x minus t. But you see what is gx? Is integral g small x dx. So gx plus t minus gx minus t is exactly integral from x minus t to x plus t g small x dx. So let me write, it's again 1/2 f x plus t plus f x minus t plus integral from x minus t to x plus t g small of x dx. So this is the final form of solution of our initial value problem. So it has two terms. One term contains f in this form, and the other term contains g. Okay. Now what is next? We will extract useful information from this. If you have just this formula, no, it is of little use if you don't imagine how does the solution look. So let us consider a couple of examples. So let me write here briefly our equation. One moment. Let me take other pen. UTT minus UXX equals 0. U of x0 equals f of x. Ut of x0 equals g of x. So this is our initial value problem. And its solution is the following. U xt equals 1/2 f of x plus t plus g of x minus t plus 1/2 integral from x minus t to x plus t g of x dx. Now let us consider the following example. Say f x equals cosine x and gx equals 0. We start from this. Then following this formula, u of xt equals 1/2 cosine x plus t plus cosine x minus t. Yeah, the second term is absent because g is 0. Now let us somehow transform it and simplify. 1/2 cosine x plus t cosine x cosine t minus sine x sine t. Cosine x minus t plus cosine x cosine t plus sine x sine t. Now this term cancels this term, so as a result it will be simply cosine x cosine t. Yeah? So how does it look? This is initial configuration of our string. So it is pi over 2 minus pi over 2. It is 1. And this is when t equals 0. Now, when t equals, say, pi over 4, for t equal pi over 4, cosine x will be the same, cosine t will be square root of 2 over 2, so smaller than 1. So it will look like this. So this corresponds to t equal pi over 4. Now, when t equal pi over 2, we go further, this term will be 0, this factor. So this is t equal pi over 2. for t equal 3 pi over 4, we'll have this situation. Yeah? T equal 3 pi over 4. And for t equal pi, it will be minus cosine t, so it is minus 1. This is t equals pi. So our string forms such waves, but this wave stays in place. It's called standing waves. Standing wave. Yes, so it's points where it is 0. They are called nodal points. So it is called node. So nodal points are fixed, and between them the string is moving up and down like this. So it is exactly what the string is doing. So if you take, say, guitar string or piano string, what this string is usually fixed at 2 points, yes, and produces some oscillations in the space between these points. Yes, sometimes there is more than one wave on the between these 2 points. Here we have infinitely long line and infinitely many these nodal points. But a little later we consider in more detail oscillation of a string, say of guitar string. It is an interesting thing to describe exactly the motion of guitar string, which is fixed at 2 points. We will do it later. Okay, and now consider another case, another situation. Another example. Another example, u of x0 equals cosine x, ut of x0 equal sine x. Yeah, so equal f of x, and this is g of x. And let us look which solution we get following our formula. So u of xt equals 1/2 cosine of x plus t plus cosine of x minus t plus 1/2 integral from minus x minus t to x plus t sine x dx equals, no, we know the first, cosine x plus t plus cosine x minus t equals 1/2 cosine x cosine t. Now let's find this integral. Plus 1/2 integral of sine x is minus cosine x. Integral of sine is it is minus cosine x. Yes. Minus 1/2 cosine x plus t minus cosine x minus t. Yeah? Equals cosine x cosine t minus 1/2 cosine x plus t cosine x cosine t minus sine x sine t minus cosine x cosine t minus sine x sine t equals cosine x cosine t, and here we have cosine x cosine t minus cosine x cosine t, they cancel one another, and remains minus sine x sine t minus sine x sine t times minus 1/2, so plus sine x sine t, which is no doubt cosine x minus t. Yes, cosine x minus t. So this means that u of xt equal cosine x minus t, but what does it mean? It means that this wave is moving in this case to the right with unit speed. Yeah? When t grows, for any t, this apex will be displaced by t. No, it is, yes, I think from college mathematics, yeah? So it is for t equal 0. For t equal pi over 2, we have this curve. T equal pi over 2, and so on. What we got is called a running wave. Running wave. So this wave which is moving. So we have two typical waves. And if you consider this solution, then our equation can be called not the string equation, but a wave equation, because this equation describes us, in particular, the moving wave. But we will have wave equation, it is general term for equation in any space dimension, not in one dimension like we are doing it for now, but in any space dimension. We will do it a little later. So for now we have just these two examples. Let us consider one more example, or a couple of examples, just to see how it can look in other typical situations. So consider example. Another example, f of x equals, say, 1 divided by 1 plus x squared. And g of x equals 0. So initial configuration of our string looks like this. It is x, it is u of x0. It is this function. It has one apex and then goes to 0 rather fast, like 1 over x squared. Yes, so it is sort of a bump. Yeah, so it is a bump function. And now solution u of xt equals 1 over 1 plus x plus t square plus 1 over 1 plus x minus t square. And all this, 1/2 of this. How can we imagine, and we have no term from g because g is 0. How does it look? So the first term is a curve like this. At the point the apex is the point minus t. And here it goes to 0 rather fast, like 1 over x squared, t squares, x squared, x plus t squared. So at this point it will be like 1 divided by 1 plus t squared. It's multiplied by 1/2. This term will be concentrated near the point t, x equal t. Yeah, and here it will be rather small, about 1 over t squared. Yeah, we consider this situation. And so these two, what we see for large t, for large t we see that this one bump gives rise to two bumps of half of its size, which are propagating with unit speed right and left. That's it. No, it is less interesting what happens when t is small. Let me do it. It's no, why not? It's interesting. It's also important. When t is small, we have this initial bump, and now we have two bumps of half of this height. One is a little bit displaced to the right, and the other is a little bit displaced to the left. This is t, this is minus t, and the sum will be here close to this, and here it will be like this. So it will be a little bit swelled, but the height will be smaller. Yes, and then after a while we'll have a formation of two humps. Yes, so then we'll see more advanced picture, and then after longer time we'll see two almost isolated humps which are going right and left. Yeah, so this is how the shape is changing in time. Let me start here. So it is a little bit like this. And here we started from this. So this is the picture in this situation. And now consider the last example here. I will devote one more lecture, or maybe it will be sort of practice, considering some other situations. So this is just immediate examples. So consider other example. Fx equals 0, gx equals 1 over 1 plus x squared. So this is u of x0, this is ut of x0. So these are the initial conditions. So initially it is 0, and then we give, say, a kick, and something starts happening. So in this case, u of xt, let us apply our formula, equals 1/2 integral from x minus t to x plus t d here x here, say dy divided by 1 plus y squared. Yes. No, this is you know, this integral, it is arctangents. Yes, so it is 1/2 arctangents of x plus t minus arctangents of x minus t. Now, let us imagine how it looks. Again, for small t, if t equals small, we return for t, let me write much less than 1. Here, small, this means less than something. Now, the natural unit is 1, because here we see no other parameters. You can write again that u xt is approximately equal arctangents of x plus t minus arctangents x minus t. Sorry. Arctangents x plus t minus arctangents x minus t. If t is small, then it is again 1/2 times 2t times derivative of arctangents x plus t. Derivative of arctangents is again 1 divided 1 plus arctangents x. 1 plus x squared equals t 1 plus x squared. So if you give a kick initial velocity, which has the form 1 over 1 plus x squared, then no wonder that initially for small t our solution will look like derivative ut times t. Yes, so this will be the shape of our solution for small t, approximately. But now it is interesting to consider what happens at large t. At large t, we have the following. Say at 0, arctangents t, for t very large, then arctangents t is equal to, is close to pi over 2. Arctangents minus t is close to minus pi over 2. So the difference is close to pi, and here is 1/2, yeah? This means that u of x t module x xt is approximately equal to pi over 2. Yeah? Now, if t less than module x, then the following thing happens. These two arctangents for large x, x much more than 1, we see that arctangents x minus t plus t and arctangents x minus t are all close to either pi over 2 or minus pi over 2. And so the difference is close to 0. U of xt is close to 0. Yes, so here it is more or less 0. And here we have at t, at x of order t, close to t, we have this gradual transition. Yes? So we have to study this function. No, let me draw this function. It is difference of two functions. One function is arctangents x plus t. It is this function. No, I'm sorry. Arctangents x plus t is this function. It is arctangents x plus t. Yes, arctangents x minus t is this function. Yes, this is, I'm sorry, arctangents x minus t. Yeah, so we have these two functions. So they are moving when t grows. This is moving to the right. This is moving to the left. Here the limit is pi over 2. Here is minus pi over 2. And we see that when it is minus t, it is t. So when we are a little bit farther from minus t and from t, here the difference is close to pi, like is written here. But we have to divide by 2, so this is pi over 2 approximately. When x is farther larger than t, much larger than t, then the difference goes to 0. Here and here the difference goes to 0. So we have this picture. So again, what we see here, so I'm sorry, so this is point t, this point minus t. We gave an initial velocity which is concentrated, this is initial velocity g of x, which is concentrated near 0. Yes, and decays fast enough outside of 0. And as a result, we see the domain where the function approaches some limit. In this case, it is pi over 2. And this domain is spreading on the whole line. Yes. So it is a typical behavior, another typical behavior of solution of the string equation. Now, I would be glad to show you the physical experiment, but maybe it is better if you do it yourself. You say take a long rope and try to oscillate its end and see the waves which are running along this rope. Or simply take this rope and give an impulse, a kick in the middle of the rope and see what happens with this rope. I think the physical experiment is more I would say convincing than say computer simulation. Of course I could do it on computer, it is not hard, but it is not so interesting as looking at a physical simulation. No, okay, so for now this portion was, the goal was to show how to solve the string equation, solve the initial value problem for string equation. Next time we consider more examples and more systematically, and I'll give you a little more portion of the theory. For now, have a good time. Bye.